Hello, everyone, and welcome to another episode of Kelly Telly. Today is a very special episode because we're going to be talking about the types of nuclear decay, which is one of my favorite topics to teach. So, hope we can understand a little bit more about the types of radioactive decay that we spoke about in the last episode. The radioactive decay, if you'll remember, is when the nucleus of a particular isotope of an atom is unstable and therefore it needs to emit either a particle or a wave to try and get to a more stable state. So let's start to have a look at the types of nuclear decay. So there's three types of nuclear decay. The first one is the alpha decay, second one is beta decay, and the third one is gamma decay. And each of them all have different properties and different some of them are particles and some of them are waves, and I'll go through all of that in this video. And we'll also return to this image because this image shows the strength of the different types of decay. So we're going to go through each of them individually. Let's have a look at alpha decay. So alpha decay, the first thing you'll see up in the top right hand corner is this is the Greek letter for alpha. And that is the symbol used to represent alpha decay. You may have seen it already in your math class. Now, alpha decay is when the nucleus of a radioactive atom ejects an alpha particle. And an alpha particle is equivalent to 2 protons and 2 neutrons, as we can see here. So this is the nucleus, right? So obviously the electron cloud would be here. That was a horrible circle. But the electron cloud would be here. And this is just the nucleus, so we're looking at just at the moment. The nucleus of the atom releases what is called a alpha particle. Now, this alpha particle is 2 protons. Just saying that again: 2 protons and 2 neutrons. Okay, so when a radioactive atom goes through a process of alpha decay, it will lose the equivalent of 2 protons and 2 neutrons from its nucleus. So that would actually affect what sort of, I'll give you a moment to think about it, right? If it's losing 2 protons and 2 neutrons, that's going to affect what part of its nature. Is it going to become a different element? Is it going to become a different isotope, or is it going to become a different ion? Now I'll give you a moment to think about that. Pause the video if you need to. Okay, continuing on, the alpha particles here are, the alpha particle released from the nucleus actually changes the element's atomic number. So because it's losing 2 protons, it changes to a different atomic number. So for example, if we had lithium, which has an atomic number of 3, and it goes through the process of alpha decay, okay? So we just do this, and we just do the little symbol alpha. If it goes through alpha decay, it ends up becoming hydrogen, because if it loses 2 protons, that goes down to 1, and what has the atomic symbol for 1? It's going to be hydrogen. Obviously, if it lost the 2 neutrons as well, that would change the atomic mass. And we'd have to calculate those. But this is an example. It doesn't happen with lithium and hydrogen. It usually happens with elements in the periodic table that have a very large nucleus, because that's the ones that help to, those are the ones that are often unstable. Okay, so this is alpha decay. It's a very weak sort of decay. It can actually be stopped by just a piece of paper. And all right, let's move on to beta decay. Explain that one. All right, so beta decay, up on the right-hand corner, you'll see the Greek letter for beta. Now, beta decay, as you can see here, is we've got this nucleus and it's releasing a single electron. So during beta decay, a nucleus ejects a beta particle, and a beta particle is equivalent to an electron. So, if something loses an electron, what is going to happen to it? It's going to become some form of ion, okay? So if we had lithium and it lost an electron, it would become lithium plus. Okay, so that's beta decay. Beta decay is stronger than alpha decay. and we'll go through why soon. But that's basically it for beta decay. Let's talk about gamma decay, which is a very serious one. So this is gamma decay. Up in the right-hand corner, you'll see the Greek letter for gamma. Now, gamma decay doesn't release a particle. Instead, what it releases are these rays. So it can release these things called gamma rays. Now, gamma rays are very deadly. Let's just have a quick read of the description that I put. During gamma decay, a nucleus ejects a form of electromagnetic wave known as a gamma wave. So these are the waves that apparently turned the Hulk into, Bruce Banner into the Hulk. Now these are very, very deadly. Now we're going to talk about in the next slide what the difference is between the different types. But just to explain this again, it doesn't release any particles from the nucleus. So the nucleus is unstable. What it does instead is to make it itself more stable, it releases some energy. Now, usually when something's going through radioactive decay, it'll probably emit all three types of radiation to try and get to a stable state. And as I said, though, this is definitely the most dangerous one. Let's have a look here. So going back to that diagram we looked at the start, the three types of decay are different, I guess, ways to put it is they're different. They have different sizes, which means that there's different levels of ways that it can affect the human body or animals or anything like that. Now, alpha decay, as you can see here, it's 2 protons and 2 neutrons. That's quite large in comparison to the others. Now, this 2 protons and 2 neutrons, which is an alpha particle, cannot even pass through a sheet of paper. Okay, it can't even get through a piece of paper. So if you had a piece of paper up in front of your face, and a radioactive atom was on the other side, you would not receive any alpha radiation. You would, however, receive beta radiation, beta decay. Now, this is an electron, which you'll remember, obviously, this is not drawn to scale. This is how many times? It's 1,800 times smaller than a proton. So it's about a tiny speck in one of these. So it's much, much smaller. It can easily pass through the paper, where the molecules of the paper atom, the molecules of the paper sample are far enough apart that it can slip through and it can affect you. However, it is not strong enough to pass through aluminium. Now, aluminium now is a metal, and as it has a larger nucleus, it is harder for that beta thing to get through, especially without getting caught up in it. Now, gamma is not a particle, so it doesn't even care about what particles are in each of these, and it will continue all the way through, but it'll even go through lead. You need a large amount of lead to prevent gamma radiation. So you would have seen when if some of you have gone to go get x-rays before, you're here and you're getting an x-ray, and the doctor will stand on this side of of some sort of protective barrier. That barrier is probably made of lead. And so as the x-ray, which again is small amounts of gamma radiation, takes a quick snapshot. As I said, it passes through your body. So that's why they can get an image so the rays pass through your body, and that's how you get an x-ray image. But the doctor, of course, is protected. You're not in any danger when you go to get an x-ray because they're in these very small amounts. But if you're on this side of the protective lead, then you're not going to get it. And the doctor does do many x-rays in a day, so it can be beneficial for him, obviously, to stay safe. But all right, so alpha decay is stopped by paper, or our skin, for example, can't even get through our skin. Beta decay can go through that, but it stops with a little bit heavier substances. And finally, gamma decay is stopped by the lead. Let's have a look at another summary. This one's straight from your textbook. Summing it all up. So an alpha particle, it has the Greek symbol alpha. It releases something which is equivalent to a helium nucleus. Now, I didn't talk about that. The 2 protons and 2 neutrons is the exact same as the atom helium, which you'll notice has 2 protons and two neutrons, making its mass 4. So it's basically like that element is releasing a helium from its nucleus. Its speed, it's 10% the speed of light, so it's pretty fast, but not too fast. And it has a charge of +2, obviously because it's 2 protons being released. Now, beta particle has the Greek symbol beta, and it releases what's equivalent to an electron. And that's 90% the speed of light. That's quite fast. And it has a charge of -1, obviously, because it's an electron. The last one, again, the most deadly, is the gamma rays. The gamma rays have the Greek letter gamma as a symbol. They release high energy X-rays or gamma rays. And they travel at the speed of light, obviously, because the gamma rays are a light wave. And they have no charge there, but they are deadly. How are they deadly? I'll go over in when we have our Zoom classes later in this week. So I hope that helped you to understand a little bit more about the 3 different types of decay. If you have any questions, please let me know or write them down ready for the Zoom class. I'll talk to you guys next time.